Good morning, eighth graders. So, we are talking about structures in our solar system, but we're focusing in on how gravity plays its role within our solar system to essentially line up everything that needs to be lined up and keep everything that's within this actual solar system that we know. So we are focusing in on two standards, but remember we kind of sort of smushed these standards together. So Middle School Earth Science Standard 1-2 and 1-3, which states that you will be able to analyze and interpret data to determine the scale uh, of objects in our solar system, as well as use a model to describe the role of gravity in the formation of our solar system. So by the end of this lecture, you should be able to analyze and interpret data to determine the scale of objects in our solar system. So, how big things are, how little things are, and how truly far apart they are. You should be able to develop and use a model to describe the role of gravity in the formation of our solar system. Um, I will show you a couple models and demonstrations. And then we have support your claim with evidence and reasoning to demonstrate that gravitational interactions are attractive and depend on the mass and distance of an object. So, a lot to go through. Make sure you have your notes out in front of you. So, back before we had all of these fancy tools and telescopes and things like that, a lot of humanity believed in the geocentric model. Geocentric model meaning Earth centered model. So this is as this picture kind of depicts, where we on Earth are here in the center and everything else, including the sun, revolves around us. Um, the early Greeks thought that planets and the sun and the moon and all the stars once revolved around us, but it was only because they had minimal understanding and minimal tools to be able to see what was truly happening out there. So we see the sun moving across our sky. We talked about this in the last unit. And so when we see the sun moving across the sky, what else do we have to think other than this, like that is moving and we are not? We cannot feel the earth rotating below our feet. A lot of learners have asked, well, what happens if the world were to stop spinning? Well, back then they didn't even think the world was spinning. Um, and all of this. So it was just very basic technologies. And by technologies, obviously, I'm not meaning like computers and all this, but like very primitive sort of telescopes, two simple lenses looking out at the night sky, observing with our eyes, not necessarily being able to track anything 100% accurately because it's all going to depend on who's the one that is actually taking the time to sit down and write and document what is happening. So, our geocentric model, we were able to eventually prove that it is not the way that the actual solar system works, or the universe. So, it makes sense for what information they had. It does not make sense now with the information we have available to us. So, we now understand that we are actually within a heliocentric model. Oh my goodness. I never yawn all morning until I get in front of this camera. So we now understand that we are a part of a heliocentric model, or a sun-centered model. This is where everything, the Earth, the moon, other planets, all revolve around our sun. So Galileo was the first one to observe this. And he observed this through the tracking of Venus. So Venus going around the sun and its different phases showing other objects would do the same. So the Earth and other planets must be revolving around the sun. The closer the planet is to the sun, the faster the orbit. Okay, he was able to watch and track Venus. It is very challenging even today to watch and track Mercury because of how small and how close it is to the sun. But Venus is kind of at that sweet point. Mars, we can do that. Jupiter, if you go and look outside, the brightest star in the sky right now is actually Jupiter. And all of this, it'll be its closest it will have ever been in like 55 years. This coming week. So he's able to track these to see, and he can see the different phases, very similar to how we see different phases of the moon, that would then indicate that the moon revolves around us and all of this. So Galileo, very intelligent man and able to observe. So he was able to confirm that this is truly how the world should be perceived, is that the sun is at the center and everything revolves around it at this point in time. And we were able to confirm that. And then, especially once we start sending people into space, then we got all of that sort of stuff. So, now, our solar system is made up of more than just our sun and our planets, but it is also made up of satellites, both natural and man made. It is made up of dwarf planets, asteroids, comets, meteorites, meteoroids, meteors, however you see it or where it is, where its location is. We have all of these things within our solar system. Oh my goodness. Huh. So, let's talk about each of those things so we can have a better understanding of what are we truly interacting with here on Earth. So, the sun. We're just going to touch on the sun ever so quickly because we've already talked about it in greater lengths. So, sun comes from the Latin term sol. So that's where it got its name. Obviously, Latin was the preferred language for a very long time. So about 4.5 billion years ago, a yellow dwarf star was born. So it is a yellow dwarf. We don't talk a lot about different stars, but on average, our sun is pretty average. It's very typical. It is kind of a run-of-the-mill sort of star. It is not a red giant. It's not a white dwarf. It's just a yellow dwarf living its best life for the last 4.5 billion years. It stands about 93 miles away and 100 times wider than our Earth itself. Okay, this large ball of burning gas is held together by gravity, with the core that is so hot that nuclear fusion actually starts to occur. We cannot see nuclear fusion occurring here on Earth naturally. We have to build fancy machines to be able to do that. So, the core can reach temperatures up to 27 million degrees Fahrenheit with a surface of about 10,000 degrees Fahrenheit. As we know and we've talked about multiple times now, the sun contains 99.8% of the entire solar system's mass. So that only leaves 0.2% for everything else we just listed on the last slide. And because of how enormous it is, it has enough gravitational pull to keep the entire solar system together, all the way from all 8 of our planets to the comets that fly the furthest away from the actual sun themselves. That is how immense the gravitational pull of our sun truly is. Planets. I'm not going to get into a lot of description with planets because we're literally going to spend the next couple of days focusing in on each individual planet. So in order for something in a solar system to be identified as a planet, okay, this is not just our solar system, this is solar systems as a whole. It must maintain three very specific criteria or limiting factors. Okay. First of all, its size. It needs to be large enough and have enough of its own gravitational force to become spherical. Okay. There are objects out in space that are not spheres. So it's big to understand that all 8 of our planets are spheres. It must orbit its central star. In our case, it must orbit the sun. And then finally, a clearing. It must have cleared its entire orbital path of any other objects of similar size. So it can have other smaller things within its orbital path, such as Jupiter technically has what are called the Trojan asteroids within its orbital path. But because of how gigantic Jupiter is, it is still the planet and the rest are just asteroids. Obviously, we have the moon within our orbital path. Granted, it then orbits around us. So it must have cleared any other objects of similar size from its orbit. And yeah, those are the 3 criteria that define a planet from anything else out in space. We do have 8 major planets that we focus in on, and that would be from the sun out. We have Mercury, Venus, Earth, Mars. Then our outer planets would be considered Jupiter, Saturn, Uranus, and Neptune. We refer to the first 4 planets as rocky planets and our last 4 as gaseous planets or gas giants. Sometimes intermixed with ice giants if we're talking about the difference between Jupiter and Saturn from Uranus and Neptune. So, how did we get to this point? Well, gravity. Gravity is the only way we got here. So, the only reason that the largest 4 planets are a crazy distance away from the sun is because if they were any closer, they would eventually get pulled too much. So, what ended up happening because of gravity is our inner smaller planets contain very, very heavy, dense materials, lots of metals, lots of rock, things like that, versus our outer planets tend to have large amounts of these lighter gases. So that's why inside the asteroid belt or closer to the sun, we have these itty bitty small but very, very dense rocky planets. And then outside of the asteroid belt, we have these gigantic gaseous planets. So that's kind of what happened. And how this happened was essentially the Big Bang, but let's summarize it into a couple of steps, focusing primarily on our solar system. So, 4.8 billion years ago, there was a collapse of a supernova. So, all of its material was thrown out into space. Heavier materials were not actually able to move very far. If you think about the difference of throwing, there's a reason why in softball your diamond is a little bit smaller. And that's because to throw a big heavy softball takes a lot more energy, so it can't go as far, versus a baseball can go much further because it's a lot lighter. So essentially that's what happened. Heavier materials didn't travel very far from the center. They were just too heavy to get flung that far. Versus the lighter gases traveled further away past what is identified as the frost line. So it's this imaginary line within our solar system where gases are actually able to stay as gases versus being evaporated off or pulled away from their gravitational core. So heavier materials and gases started to combine again to create our sun. So some gases were able to be pulled into what is now our sun because they're a lot lighter. They're a lot easier to pull thanks to gravity. That materials for planets started to combine and they started to clear their own personal orbits to create the planets as we know them today. So we're about like in this diagram, we're about like step 4-ish. So planets closer to the sun are warm enough for the materials to condense into solids, and then the planets past the frost line form these cores much quicker, but the cores are primarily frozen materials, and then they're able to pull in some of those gases, and by some I mean a lot, to where we then get to step 5, or the planets as we know them today. All of our planets were literally just formed from garbage. What was flung out from the supernova that couldn't survive within its actual capacity. So, yeah, to where we get these 4 very small but very dense planets very close to our sun, essentially because a majority of their gases were vaporized off because of the heat of our sun. And then we get these 4 gigantic gas giants past the frost line, that are just able to hold all of these lighter materials together because there's nothing there to evaporate it away, and things like that, to where you get these very distinct size differences. So the way that our planets are laid out is very particular. They have figured out where they need to live within their own personal zones, to where even something as small as Mercury isn't being pulled in by the sun, but it's able to stand on its own 2 feet in its own area. And all of this. And as we know about gravity, when you have this size difference, so something of very great mass and something of very little mass, their gravitational attraction already is just not as strong. And then you add that distance that is between the sun and Mercury. And it continues from there. So if you were to put something of far greater mass much closer to the sun, what do you think would truly happen? So the idea that we always throw out is, what if Venus and Jupiter were to switch places? Venus is about the same size as the Earth. It does have a lot of gases, but they're more of these heavier acidic gases, and all of this. So we have those super close, but it's able to kind of stay where it is, but it's on like the much smaller end of our planets. Then we have Jupiter, the largest planet of them all. Lots of gas, lots of gravitational pull, so much to where it has 80 plus moons, versus Venus doesn't have any moons. It's not big enough to really attract any other moons with where it is at, and all this. So what would happen if they switch places? Well, essentially, Venus would start to fly off somewhere because it is far too small that far away to have any sense of gravitational pull toward the sun. It's just where it is. Versus Jupiter, different story. 2 very large masses, now very close together. What happens when 2 very large masses get close together? they get sucked in towards each other, because remember, gravity is very similar to a magnet in that sense. So that's what would happen. Venus would go away. It would probably go out somewhere toward where like Pluto and the Kuiper Belt are, because it doesn't have that gravitational attraction. And Jupiter would get sucked into the sun. So that's why these very, very large planets occur where they do, so that they are just enough at arm's distance away from the sun to kind of be touched and pulled by that gravitational pull, but still far enough away to where they don't get too close and smack together. So that. This is a demonstration with magnets. It's not the best demonstration. There is something else that hopefully we will be able to do in class, to be able to show you. And once I have the proper materials and whatnot, I will get it recorded. But essentially, you can kind of show how gravity and magnetism are very, very similar, and how they can kind of pull each other in. And why things are sitting in the perfect little spots that they're sitting. So that is it. I know the video isn't going to play if I try to play it over this, so make sure that you go and you actually watch it from the folder. But this is the end of whole group. So make sure that you have completed your whole group notes. Some of the questions is going to rely on you taking the information that you've learned today, plus the prior knowledge you've already gained throughout this unit, to be able to answer and then proceed into your independent work. So let's talk about satellites. Satellites are one of the things that appear within our solar system that it's the only thing that can be considered both natural and artificial. So a satellite is an object that orbits another object within space. Excuse me. So when we're talking satellite, we are talking about planets and moons and asteroids. These are all satellites around, at minimum, the sun, but can also then be orbiting around different planets like moons and all that kind of stuff. But then there are artificial or man-made satellites. These are the machines that we launch into space to orbit Earth and other planets. And these things essentially are recording data for us here on Earth. So artificial typically means man-made. And then natural are our planets, our moons, and our asteroids. And we need to remember, thinking back to our first unit, moons can have an impact on our planet, just like impacting things like tides and werewolves and things like that. So keep that in mind when we're talking about natural sorts of planets. Dwarf planets. So this one is probably more relative to your grown-ups or to me and my generation, because this was a new classification that NASA and other astronomers did not develop until about 2006. So up until 2006, the only things we really truly understood about our solar system was that there were 9 planets orbiting around the sun. We knew that there were some asteroid belts and things like that, but we didn't know much else. In 2006, we identified another potential planet. I want to say it was Ceres. Yeah. And that's when we discovered the fact that we needed to classify our planets in one way, and we need to classify other things another way. So that is where we came up with the criteria of a planet. the size to where it's somewhat spherical and the gravitational pull. It has cleared its orbit and it revolves around the sun. So that. Well, because of the discovery in 2006, they developed a new category or subcategory of planet, and that is dwarf planet. To where some of the criteria or the box that kind of keeps them very limited, what their criteria is very similar to the criteria of a planet. That's why it still has planet within its name, but it's not one of our major planets. So dwarf planets still have to orbit the central star, so our sun in this case. It must have enough mass and gravity to be spherish. I say spherish because we do have a dwarf planet that is shaped more like an egg. But where it starts to differ is that dwarf planets tend to be similar in mass with the other things within its orbital path. It has not necessarily cleared an entire orbital path for itself. And it does sometimes, like in Pluto's case, cross over other paths. So Pluto crosses into Neptune's orbital path every once in a while, to where technically when there were 9 planets, it was Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, and sometimes Pluto, sometimes Neptune, and then vice versa for the end. So it switched depending on where we were in its orbital path. So things like that. So dwarf planets don't have to completely clear their orbital path, and they don't necessarily have to be the biggest, baddest thing in that orbital path. They just have to be similar in mass and have some distinct features that set it apart from everything else within its orbital path. So that is when, unfortunately, Pluto was demoted from a planet to a dwarf planet. And since then, we have discovered many, many more dwarf planets within our solar system. And we keep finding those dwarf planets within these areas. So some of the other things that are being held in place by our sun's gravitational pull include our asteroids. Asteroids are small rocky bodies that are orbiting the sun. They are not necessarily spherical. If you go and look at a pile of rocks here on Earth, it's what the asteroid belt looks like, just a bunch of nonsense. Now, we have found what keeps asteroids a little bit more like in their own little thing, is that they mainly stay within 2 areas. Most of our known asteroids are found between Mars and Jupiter in what we call the asteroid belt. So it is the space between Mars and Jupiter that a majority of our asteroids just kind of hang out. It looks very similar to this sort of diagram, where you can see where their orbital path could be, but you have some stragglers that are a little bit further off from that orbital path. Now, the really cool thing, and where we can kind of see gravity at work, is within this asteroid belt, and that's because asteroids within this belt very, very, very seldom crash into each other. They don't stick together, they just stick within this ring. And that is because of the gravitational pull from the sun and the gravitational pull from the gigantic Jupiter. Essentially what's happening is Jupiter and the sun are kind of having this like tug of war sort of battle, and the asteroid belt is that flag that hangs in the middle. The sun is pulling everything toward it. Jupiter is pulling everything toward it because it's bigger. This is how Jupiter got a majority of its moons, is flying asteroids that get sucked into its gravitational pull. So they don't clump together. They stay separate individual asteroids within this belt. Um, in all of this, and that's because of the gravitational forces between these two very large bodies of mass. Now, you do notice that there are what are called Trojan asteroids that fall within Jupiter's orbital path. And again, this is all playing off of gravity. You'll notice that they don't get very close to Jupiter itself, but again, because of the pull from Saturn and Jupiter and the Sun, this is kind of just where they get stuck. Um, so, yeah. There is another asteroid belt, but we don't call it the asteroid belt because that'd be confusing. We call it the Kuiper belt, and that is found just beyond Neptune. This is where Pluto lives primarily. So the Kuiper belt is another very similar shaped asteroid belt that, because of the pull from the sun, which, yes, very, very far away, but then the pull from any outer sort of bodies in other solar systems, keep these rocks essentially orbiting around Neptune and the sun, just way out there. So, those are the two asteroid belts, and that is where we have been discovering more and more of our dwarf planets. Oh my goodness. Our dwarf planets. Because something just starts to set it apart to where you see just something different within those areas. But this is where we can start naming and identifying some of these objects without giving it a true planet name because they haven't cleared their orbital path. They're stuck within a big old community. Comets. So, comets are these mixtures of rock and ice and dust that are loosely held together by gravitational attraction. Oh my god. I so sincerely apologize. That are loosely held together by gravitational attraction, and they have these very long elliptical orbits. So if I were to get in here and draw, so like we have our sun. Okay, the sun is yellow. Okay, now these elliptical orbits seem really weird, and that's because they come in super duper close to the earth, to the sun, sorry, and then they fling all the way out here, and then they come back in, and they do that. Versus every other elliptical orbit is more like, beep, a little bit more like put together, sort of a thing. Okay. Closer, and they maintain a very like they maintain a size that just it's more rounded. It's still elliptical, but it's more rounded. And all of this. So comets make these really big passes. They can live anywhere into the Kuiper belt out to, oh goodness, all the way out to the Oort cloud, which if you were to imagine like a marble. The Oort cloud is the very outside of the marble, and then the sun is all the way in the center part of it. The Oort cloud is that very outside layer. So, but a lot of comets live out in that direction, but every once in a while they come in toward the sun and light up our night sky in different ways. So, a comet, the gravity of a planet or star, in this case our star, can pull comets from their homes in the Kuiper belt or the Oort cloud. The tug itself, or that gravitational pull, redirects the comet toward the sun, and then the path of the redirected comet looks like this long oval shape. So that's how we get this really long ellipse. As the comet is pulled faster and faster towards the sun, because as it gets closer, the gravitational pull gets just that much stronger. It swings around behind the sun, and then heads right back to where it came from. Um, some comets, the ones that we don't see ever again, can nosedive essentially right into the sun, never to be seen again. But then you get comets like Halley's Comet that essentially does this boomerang around the backside of the sun and flings right back out to the Kuiper Belt. That we see the comet when it's coming by our planet or close planets. Oh my gosh. This is ridiculous. I apologize. So we see the comet coming in, um, because essentially what starts to happen is it starts to glow because of different atmospheres and things in the space where it's traveling, that start to burn it up and form this light streak across our night sky. So, and that is because we have things like the solid inner core. It's mainly a brick of ice that has some rock and dust inside of it that starts to absorb all that thermal energy. So the heat you can actually feel. And then it starts to develop this bright tail that trails behind it. The ice. I don't even feel that tired. This is silly. The ice turns into gas as it gets closer because the gas and dust move away from the nucleus, making this glow, and the glowing nucleus becomes what is called a coma. Our sun technically has, like, it's called a corona, not a coma, but same sort of idea of this outer, like, halo-y ring of light. So those are comets. Um, they're a very odd sort of structure within our solar system, but they do still follow very similar sorts of principles and expectations of an object in our solar system. Final items that we see within our solar system, um, are the same thing with three different names, depending on their location. So we have meteoroids, meteors, and meteorites. We tend to talk about them as the meteors, that streak our night sky. So let's talk about this. Starting out in space, because this is where everything originates. This is where we call it a meteoroid. This is just a small rocky particle that just moves through space. It's that leftover gunk from that supernova explosion. Um, it can be anywhere, and this is what sets it apart from like an asteroid or a comet, is that it's actually really, really small. It ranges anywhere from the size of a grain of sand all the way up to about the size of a golf ball. Okay, so meteoroids are when they are out in space, living their best lives. Now, if a meteoroid gets close enough to a planet's gravitational pull, it starts to get pulled in. Once the meteoroid enters into an atmosphere, we get this streak of light, and that is when it changes from a meteoroid to a meteor. We have meteor showers all the time. There's one that always happens around my birthday in April. And it's essentially just when this like space dust starts to enter into our atmosphere. So this small rocky body from outer space entering into the atmosphere, becoming incandescent, or starts to get really hot and lights up, as a result of the friction, and it appears to be this streak of light. Now, as it's moving its way through our atmosphere, meteors tend to burn up. That is the only job of some of the layers of our atmosphere, is to essentially take those meteors, burn them up so that they don't make their way down to Earth and, wipe out an entire species. Things like that. But as the meteor makes its way through the atmosphere, typically something makes its way to Earth's surface. And that is when we finally call them a meteorite. So when space, rock, and junk finally survive their trip through the atmosphere and make it to the surface of a planet or another object, this is when it's a meteorite. So meteoroid, meteor, meteorite, all the same exact thing. It's just where is it in comparison to the Earth? So, or planet. So, those are the structures of our solar system. Hopefully, all of that kind of made sense, and that all of this is only because we have our sun, or there's a central star that is constantly pulling things in toward it and keeping it also kind of where it needs to be. So, yeah. If you have any questions on the notes, reach out. We want to be able to help and teach and all of that. So just let your educator know. Oh my goodness, one more yawn. If I haven't yawned enough today. So there you have it. If you have any questions, please reach out. We want to help you understand this. Yeah, check at the end of this lecture and notes. And I'll see you guys next time. Thank you.